Alrighty. Now, the toroid is basically a solenoid that is wrapped into a circle. So it is circle coils of wire wrapped into a circle, and it looks like this. So this would be the solenoid with the wire, the current coming going into the page, and then coming around to the other side where it'd be coming out of the page. And looking at this, then the equation for this, if we talk about a solenoid, we just saw is the magnetic field in here. These green arrows would be mu naught I, and then times little n, which is number of turns per unit length. So that is the number of total turns divided by the length. In this case, the length, as we go around, is a circle. And so that's why the equation for a toroid is the same as a solenoid, effectively, but divided by 2 pi r, where B field, this is the strength for the magnetic field in a toroid. It never comes up, but potentially it could. So at least I wanted to mention it to you. I don't think I have anything here. Nope, blank page. Okay, magnetic dipole, last little part. So when we talk about this, if we have a magnet that could move in through a loop, it would induce a current that would be going this way. And the ability to do that, this is called the magnetic dipole or magnetic dipole moment. And so the field's up through the loop, but then Y. And if you imagine the loop that has a current running through it. So they're talking about a loop here with a current running through it. It's going to behave exactly like a magnet with the north end here and the south end here. And that's what we're trying to explain is why is that going to happen? If the current runs this way, why does it behave like a magnet with the north end here and south end here? And to answer that question, we would look and say, okay, here is the current coming out. And then if you put your right hand in the direction of that current, you get a magnetic field. This is the circle that is centered on that. And the magnetic field would sweep around and come that way. And if we have point our thumb in the direction of the current, then our fingers would swirl around this way and the magnetic field would point that way. And so we're doing that same thing we've done before with E fields a lot, where this portion cancels this portion in the X direction, but the Y portions add. And so the full equation for that turns out to be this equation. But the distance a long way from the axis, the radius of the loop really doesn't matter, and that makes r in the denominator pretty unimportant. So this would be the equation for one loop if we ditch the r. And then if we multiply just by pi over pi, which isn't necessarily something you would have to do, but if you look, then we have pi r squared, which makes area. And then we have INA, which is what we call the magnetic moment. You remember that when we were doing torques on current carrying loops from chapter 29. This has that funny symbol mu, that they call it. So then you get that crazy equation where it's mu naught mu over 2 pi z cubed. And that's the equation for magnetic dipole moment. And looking at that, they give us these opportunities to look at the problems, and they say the figure shows 4 arrangements of circular loops, R and 2R, centered on vertical wires. And looking at that, we would set up like this. And all we really need to do is do the same thing we were doing with the Amperian loop, where if you curl your hand this way, your thumb points down, and curl your hand this way, your thumb points down. So those two add together. So that's why that's 2. If we go here, we would say we curl your hand this way. This one, we would have our thumb pointing down. For this one, we'd have our thumb pointing up. Total be 0. They cancel. Here, thumb points up. Here, thumb points down. Here, thumb points up. Here, thumb points down. So that's why 0 and 0. And then here, thumb points up. Here, thumb points up. Here, thumb points up. Hey, Quinn, how are you? I'm making videos for big kids. Do you want to say hi to the big kids?
Yeah.
Say hi, big kids.
Hi, big kids.
There you go, Kilo. This is a picture for one of the problems on WebAssign, and we're good.